Hello, welcome back to our channel. And this time we have got you another new digital logic circuit that we wish to understand its response. So as you can see, this digital logic primarily consists of three blocks. Here you have got this multiplexer, which is really 2:1 mux. Okay. And the logic function of this mux we need to write, for example, the output, let's say here it is y, so y can be written as a bar uh, 0 or a bar 0 or a 1, right? Or it can also be written as a bar q bar or a q. So because 0 is connected to the q bar and 1 is connected to the q. So this is the Boolean expression for this multiplexer. So let me write here mux. And then you have got this NAND logic. This is a NAND gate. Then you have got this a D flip-flop. So this is your D flip-flop. Okay. So the output of the D flip-flop is Q and Q bar. You have got the clock, so it has a frequency F, which is not defined. And this is your select line for the multiplexer. All right. But what is the question here? So the question here is we want to draw the state diagram for this circuit. So what is the state diagram is basically tells us the transition of the outputs of the circuit from previous state to the next state. I repeat again, the state diagrams illustrates us the transition of the output of the logic elements from its previous state to the next state. So for example, you get to see that you have a Q is the output of the circuit. You can also have the Y here, which is the output of the multiplexer. And here, let's say, you can also call it, let's say, X. So X is also an output of this. So all these outputs, Q, and hence the Q bar also, and even the inputs also. So input is D here, okay? So all these inputs and outputs have their previous states, and when there comes a clock, usually a digital waveform switching between logic 0 and 1, when that train of pulses come, these elements, outputs and inputs change their states from previous to the next state. And that's what we want to analyze in this circuit. So let me explain you how we can do that. So we assume that the initial state of the D flip-flop output, that is Q, is equal to 0. And then we also say that the initial state of the D flip-flop can also be logic 1. And similarly, when we say Q equal to 0, it means Q bar will be equal to 1. And here Q bar is equal to 0 because we assume so they are the complementary output. Okay, so let me just limit our discussion by observing the changes in the uh, main output, and we will assume that we can then derive the complementary output as well. So now I assume here there is the initial state of, let's say, logic 0. Okay, and for logic A equal to 0, I know that the in data line present at this input, that is 0, gets connected to the output. And initially I assume I am in this state, that is Q equal to 0. So here I would say Q equal to 0. That means Q bar is equal to 1. And for A equal to 0, the Q bar gets connected to the output through this multiplexer. So I will say this logic line, that is Q bar, which is at set to logic 1, appears at the output. Then this one is here, and here is 0, that comes here. The output of the NAND gate then becomes 1 because this is the complementary of AND. Then 1 comes here. Okay. So what we understand, when the clock has arrived, this is how the transition cycle is going on, and this D has input 1, therefore Q becomes 1. So from previous state of 0, the Q now becomes 1. So I would draw the transition like this. From previous state of Q equal to 0, I have got the new state, that is Q equal to 1. And this happened when logic A equal to 0. I say again, logic A equal to 0, it means Q bar data present on the Q bar, which is logic 1, gets connected to the output of the mux, which comes then to the input of the NAND. Here the Q is equal to 0, that appears as the second input to the NAND. Output here becomes 1, that becomes 1 as a D input. And because of the clock, you have got the new state of Q, which was initially 0 right here. It now became logic 1. So that is our first state. Okay. So what we can understand, we have understood how the transition of the state is being made. Now let us understand the second condition when Q is equal to still 0 in the present state or the initial state. That means Q bar is equal to 1. But now for A equal to 1, the data line Q, which has 0 at its input, gets connected to the output of the mux. So 0 comes here, which is one of the input of NAND gate. 0 also appears here because Q equal to 0. Output here becomes 1. Here D becomes 1. And the Q, because of the clock, your Q becomes from 0 to 1 because D equal to 1 here. So you again say that I have got this line that is coming from transition from Q equal to 0 to Q equal to 1, and this happened for A equal to 1. So I hope you are following me with what I'm explaining you here. Now, let us say we are in the state of Q equal to 1. So this is finished. Now we are in this state. We are assuming the present state or initial state of the D flip-flop output is Q equal to 1. That means Q bar is equal to 0. And for A equal to 0, if we apply logic 0 here, which line will get connected to the output through the mux? The Q bar line comes here. That is logic 0 comes here, which is the input here. Then 1 is here. Then output here is 1, D is 1, and the Q remains 1 because the D input is 1. So present state of output is 1, and the next state of output is also 1. So we can say that for A equal to 0, present and the next states of the D flip-flop output remain same. Okay, now it's time to analyze the state diagram or state transition for the final output, or that is A equal to 1. Q is assumed to be in the initial state of 1. That means Q bar is equal to 0. Since A equal to 1, Q gets connected to the output through the mux. And logic 1 comes here. Here is logic 1. Here is logic 1. Output here is now 0. D input is 0. And obviously Q transitions from logic 1 to 0 because input D is equal to 0. So here we can say that now we are transitioning from Q equal to 1 to Q equal to 0. So here is the direction of the state transition. And here we'll say this happens at A equal to 1. Okay, so I think we have analyzed all these states. So this is called as state diagram. If I give you an exercise to draw the state diagram for Q bar is equal to 0 and then Q bar is equal to 1, can you draw this? You have to again assume a equal to 0 and a is equal to 1. So you can just tell me from when q bar is equal to 0 and when a equal to 0 and 1, how the transition from one state, present state to next state gets delivered. So basically, this state transition diagram or state diagram helps us to understand the switching of the logic levels at the inputs and outputs in the digital system design. So when you design logic design, digital system design, for example, a vending machine, or you are doing any embedded system using FPGA or ASIC or something, and so you need to design a logic. And when it is a complex logic, you actually have to understand the state diagram. Okay, so we will do more complex analysis as we'll move ahead, but hope you like this video. So here is your clock, and your circuit can work at the positive edge of the clock or at the negative edge of the clock. Okay, depends on your logic levels that you have chosen. So hit the like button, share this with others for a wider reach. Stay tuned for more engaging and informative contents like this. Till then, wish you happy learning.